Hello. Oh, can you hear me? Wait, yes, you can. Good morning. Good morning. Oh, this is just a strange view. Okay, I'm off in space. Good morning. Good morning. I'm looking at the. Good
Good
morning.
morning.
Oh, I heard a voice. Was that? No, that was not it. Wait, I heard a voice. Well, all right. Well, you did it again. It's the same class again. Is it Pushpita who does that? Or somebody. I totally appreciate the voice, and I'll never know who it is. I guess. I guess it'll be the ongoing thing. But okay. But you can still apply for point. Okay, I'm saying hello, hello. Also, I can't see anybody because this crazy view, which I'll change in a minute. So, but good morning, Eric. I see in the chat. Good morning, Tree. Good morning, Maya. Yes, sorry. Good morning, Loani. Good morning, Lena. Good morning, Sharon. Good morning, Munera. Good morning, Sydney. Good morning, Pushpita. Good morning. Oh, it's Ashley, right? Oh, yes, yes, yes. Okay. And I knew that, or I will start knowing that. Yes, thank you. Awesome. Okay. Noted. And good morning, DJ. And good morning, Haley. And good morning, Munera. Why do I feel like that's a double? Oh, because yeah. It is a double. Oh no, it's a multiplayer co-op for Munera, I think. I don't know. Anyway, good morning, Erica. Good morning, Sarah. Okay, and I'm looking. Oh, and there's still more people coming. Sorry. Okay, and now I'm just looking at the visuals, and I will switch the visuals in a second. But good morning, Sharon, Loani, DJ, Tree, Munera, Sarah, Kayla, Manpreet. Good morning. Okay, we're almost there. And Fabricio. Oh, love it. That's a step up. All right. And of course, Sydney, not a course, but yes. Okay, love it, love it. And lastly with the chat, Duran and Kayla and Manpreet. Good morning. Okay, and here comes Emily. All right, let's get this party started. Um, and good morning, Alice. Okay, awesome. Yeah, this view is ridiculous. Okay, I want to get to like this. I want to get to what's on the board. I just want to ask you quickly, maybe put in the chat. I'm finally like the schedule is starting to coalesce in my mind. Well, we don't have class this Thursday. Okay, that's weird. I mean, it's not weird, but I don't know where that's going to get made up. So I'm going to tell you right now, the unthingy things that came in, that were due this morning. Of course, if you handed it in like by last night, then you got it back already. If you just handed it in, of course, you haven't gotten it back yet, but you're fine. We're going to discuss the unthingy things. The thing is, in all the classes this week, the idea was to discuss the unthingy things in the second class of this week. But you guys don't have a second class of this week. That's a little confusing to me that you don't know the others do. I mean, I'm sure it gets made up somewhere. Um, Long way of saying, please forgive me in advance. We are going to discuss that in the next class. But I guess that's not for a while for you guys. Like, we don't have class again after today. We don't have it again until a week from this Thursday, I believe. Correct me if I'm wrong, but I believe we do. Right. I believe we don't. Like, right. That's what I'm saying. Right. Okay. I see Sarah. Thank you. And Sydney. Thank you. Right. Oh, and you have a homework question. Okay. So what I'm saying to everybody, and I want to move on in a minute. Right. I believe we don't have class again until a week from this Thursday, which is a little odd. So, but that's the class where I'm gonna discuss the unthingy things homework. Like, what was the purpose of it? What does it have to do with the class? What was I looking for? All that. We won't discuss that for another week. I apologize. But I will tell you right now, and it looks like at least one person has a question. I will tell you right now, let me remind you. First of all, if you didn't get all the points or you didn't get all the points you wanted, you still absolutely can. Like, this is I'm trying to send a message. This is an ongoing back and forth between you guys and me. Like, it's draft and revision with anything that you want. So if you didn't get all the points on the unthinking thing, like, definitely look at the rubric to get a sense of why. You'll have an even deeper sense of why when we discuss it explicitly in class. and you'll still have time to revise. But I'll tell you a couple of quick things, but it's not about right or wrong answers, especially not that one. And it's not about, and that one, it's not about five-step method. But I'll tell you very quickly right now, if you're looking to get more points on it, if you don't know why you lost points, I mean, please read the rubric. And for the homework that's coming in the future, always look at the rubric first before you do the assignment. It will help. It's not a perfect solution to anything, but it will save you a step or two in trying to anticipate what I'm looking for. I will tell you with the on thingy things, if you got fewer points than you were expecting, I mean, even if you worked really hard on it and you thought really hard about it, which is evident in many, many cases, people worked hard, said really creative, cool things. Um, but the reason they might not have gotten all the points is, okay, first of all, on that one, on, okay, I'm talking to you on homework 1B, if you want to get more points, wait, I'm looking at the chat. All right, okay, wait, there's a lot going on in the chat. Let me try to land this plane quick and then I'll address the things in the chat. With homework 1B, it it's the one time that it's not about the five-step method because it's not quantitative, but it is very much about self-sufficient document. Like even sort of more so because it's such a sort of personal, like exploratory thought and unusual and unexpected assignment. The first thing is self-sufficient document means like really look at your piece of paper, look at what you wrote. Ask yourself if you gave this piece of paper to someone who's not in the class, like a smart person, a respectful person, but someone who's not in the class who doesn't know what the assignment is or doesn't like care about physics or something necessarily. If you gave it to your boyfriend or your girlfriend or your mom or your dad or a person in the MSRC or etc., like, would they really know what it is you're trying to do, what you're being asked? Could they really follow the whole thing just from reading your paper? I want to admit or say, and this is not critical, I'm just trying to get you all in this habit for a lot of reasons. It's harder than it sounds, especially with an assignment like this. Even if you identified like that thing one was a pencil and thing two was a calculator or something, if you just, and I'm talking to everybody, I'm not just talking to people in the chat, if you just launch into it and just say something like thing one is a calculator, thing two is a pencil, task two is impossible, no one would know what that means unless they were me, right? Or unless they had the assignment in front of them. You really want to back up, especially on a thing like this, and say something like, I was considering given two objects, like this one and this one. The question is, can I do this or this or that? Like really frame the whole thing so that it could be a one-off. If you follow it, that's one thing that where people might have lost points in or not gained all the points in self-sufficient document. The test is anything else or any other context needed to navigate this document? And the hope, what you're hoping for is no. Okay, that's number one. Number two, in this one in particular, if you look at the rubric, I really do want pictures and diagrams. Like show the different tasks one by one somehow. Like either like what you did with your hands or a graphical representation or something like try to help me visualize what you were trying to do. And of course, if they're possible, it should be visualizable. If it's not possible, maybe you're coming up with some diagram to show why it's not possible or something. But I really want, and again, if you look at the rubric, please don't just say possible, impossible, possible. Like I want an exploration of each one, or we're looking for an exploration of each one if you want to get all the points. And then finally, again, I'm trying to say this quick because we really will talk about this in 4 days and whatever it is, 8 days, and you will have time to get more points. Please don't panic or anything like that. But the other thing is the very last question, like what is a particle or what is meant by a particle? That's ultimately the purpose of the whole thing is to get us to think about that. That's how it relates back to the course. And that's also two things apply to that question. Like one, this business of self-sufficient document applies because of course you could go on the web and there's all kinds of stuff written all over the web about particles and subatomic particles and like photons and all this. It's all fascinating and it's not cheating or unethical to go on the web and look up all that stuff, but it's not what we're looking for. What we're if you use it to help, get your thoughts going, great. But we shouldn't be just suddenly introducing new ideas. Like, don't just start talking about photons or wave particle duality or something like that's a whole other world of thought that we haven't engaged in yet. What I'm asking for when I say I'm asking for your perspective on what might be meant by the word particle. But what I mean is based on what you just put yourself through with the five tasks. Like the ultimate standard for that last question, it doesn't matter whether you say something I think is right or wrong. It would be hard to be dead right about that question. But what I'm asking is, can you come up with an answer for what is meant by a particle that would be different if any of your results for the impossible possible things were different? Like, can you sort of, in other words, like summarize, not summarize, but like if any one of the tasks that you found to be impossible were in fact possible, presumably that would affect your final answer to particle. That's what I'm looking for. Something that somehow comes up with a concept that seems to embody what you just discovered with doing stuff at your desk. So not like like an intuitive, reasonable discovery that, in other words, don't even worry that the word is particle. Say, if we were to make up a word to define the type of object that you just played with, like what would the properties of that word be? Okay, I'm gonna look at the chat. So there's someone here. Oh, sorry. So again, there's always plenty of time to get more points. Everything you do is a draft until you get better and better at knowing what I'm looking for, what the course is looking for. And so please don't be upset or angry at yourself or me about if you didn't, or just get in the habit of looking at the rubrics in advance. So I'll say more about that in a week and a half, but you could get a jump start on it till then or not. Um, but the main thing that will be due when we come back together, wait a minute. How's this work? Oh, your math. Well, that's interesting. Hold on, I'm just thinking. Yeah, your math homework, like your homework number two, which is big, and it's like all these math exercises and stuff. That's not due till you know two, 2 weeks from now. So you have time to do that. And what I really want to get to today in class is I want to get more into all that math that I'm asking you to do. Okay, all right. So now I'm going to look in the chat. So today is more about math and going back to like the calculus stuff that we started 2 days ago. Okay, but I'm looking in the chat. Hold on, and I'm going to change the view on the screen again. Um, Oh yeah. Okay. So there's one chat question about I for that and so please with these assignments, like look in the rubric really before you do it. Like there always from here on will be a rubric before you do it. For that one, and I think I put it in Google Classroom. That one I was not looking for five-step method. That's very unusual. It's just for that one because that's a conceptual, non-quantitative assignment. So I wasn't looking for five-step method, but I absolutely, yes, was looking for full sentences, complete sentences of your words. Like the ultimate standard always is self-sufficient document for what all the implications of that are. It means you are presenting a piece of paper that someone could read on its own and follow and appreciate what you're saying. So it has to be complete sentences and all that. Yes. Okay, that's one thing in the chat. These are direct chat things. One person saying, "Oh, and good morning, Fabricio." Okay, good to see you. Love the animated avatar. Okay, one person saying they're trying to complete a game turn, but each time, even when they click submit, it doesn't submit. So obviously, this is just one person having one particular issue, but this does happen and they're asking if they can email me. Okay, this happens from time to time. Let me tell you all, if you ever know in good conscience that you're trying to submit something, but it just keeps like not submitting, 9 times out of 10, what that means is that your Google Drive is full for other reasons. Uh, so unfortunately, what that often means is you have to independently go and do something to empty your Google Drive. Like I don't know how I mean, you have to, or then you're running out of storage space and you have to do something about that. That's often what that means. Um, so please check that first. Um, As to the larger question of whether you can email me to preserve to receive credit, in general, I have to say to people, so I'm not trying to shame anybody, and it's a very legitimate question, and I totally get why it's a direct chat question. In general, sending me work by email is not, it doesn't work. Like in general, I have to say no to that. It just gets things get it's very hard for me to then to get the grade into the system for you. It's hard for me to give you the proper credit and things get it's hard. So in general, my answer is no. And with the game turns, I don't know that it's worth you losing that much sleep over it. I know who the particular person is who's asking me this. If this particular person, if you want to email me this time until you get it worked out, I could probably work out something for this small little thing. But in general, to everybody, that's not going to work. Um, Okay, nothing is 100%, 0%, but it's not a good strategy in general to email me. Oh, to email me work. Okay, but I hope you understand. But try to clear your Google Drive. Okay. All right, I'm gonna go on. I'm looking at the chat. Yeah. Okay, this is really worth me stop. I will move on. But someone, oh, and there's also a question. Okay, I see the hand. I'll get you in 1 second. I'm also going to change. I know this view is super distracting. But someone's asking in the chat. This is very good for everybody. I'm actually going to read the words. So, for all of our homework moving forward, do we need to explain everything in a sense where it is broken down plain and simple and not in a sense of academic language, but rather explain it how we would to someone who doesn't know physics? That's a beautiful question. I hope you all heard it. Basically, are we supposed to be breaking our explanations down into like common English? Yes. Like everything I'm saying right now, I'm slowing down because that's really, and I think that may be surprising to maybe that's why some people are confused. That might be unusual. Now nothing is 100% like everything is, there's exceptions, and I'm not perfect and you're not perfect. And, for example, I'm a big fan of the 5-step method, but this particular homework, we didn't use the 5-step method. So there's always a little bit of, you know, room for imperfection and interpretation. But when in doubt, if you're looking for a rule of thumb, if you're looking for like basically what's the tone of this class, yes, unless otherwise specified. What I'm really trying to train you guys, what we really want to be trying and struggling to do is break everything down to as basic terms and as basic language as possible. That is the goal of all these assignments and self-sufficient document and 5-step method. That may not be clear to everybody. And it is not like all science classes in that way. But yes, what I'm trying to train us all to do is break things down to steps that are and words that are small enough that normal people can follow them. And that's so important. Let me tell you, that is not because I'm trying to make this class easy or that I'm trying to not educate you in a sophisticated way. It's not because this material is not sophisticated. It's not because it's supposed to be like the watered down class. It's the reverse. I promise you that all my physics heroes, what I learned from physics, my heroes that got Nobel Prizes and all this kind of stuff, what they were known for. Like, I'm not making this up. It's not about condescending to you or to me. It's about that this is really the art of physics, is that no matter how sophisticated and advanced physics gets or looks or seems, we're never trying to be overly sophisticated. What we're always trying to do is show that even the most surprising, sophisticated, detailed ideas about the universe, we believe them because they can all be broken down and traced back to fundamental notions that we all share and experience every day about the world. The thing of physics is that we take basic, common, intuitive recognitions and we move baby step by baby step by baby step, logical inference from logical inference to logical inference until we cannot escape super surprising, unexpected conclusions. The whole idea of physics is moving from the idea that, like, wait, the sun rises every morning in the east to, oh my God, then it must follow that that the universe started with a big bang or that they're black holes. We don't believe all the crazy stuff because we want to be crazy. We believe it because we believe it follows logically from simple ideas and simple words that everybody would agree with. So, so what's hard about physics is breaking it all, is keeping it always honest and tethered to fundamental common human ideas. That's what we're trying to do here. Yes, I mean, I'm going to move on, but that's what all my rules and five-step method and self-sufficient document is all about. Are we constantly only saying things that we actually understand, that actually come from basic ideas about the world that we could converse with other people who have basic ideas about the world? If you can explain differential equations in basic terms, that means you really understand differential equations. And that's what I'm going to get to in a minute. So I promise you this, I'm excited that someone sort of picked up on that. That's the idea, is to break it down, break it down, break it down, comma, yo. And it's not because I'm trying to make your life, it's not because I'm trying to rob you of education. It's because that's what it means to truly understand something, is to be able to write a children's book about it or like whatever. Do you see what, like, yes. So yeah, I'm going to move on. And so if somehow you've been trying to sort of do my class and you're not you, whoever, and you're like, I think I'm being a good student. I'm doing all the things I did in chemistry and biology. Why does he keep tearing me down? Why does he keep tearing me? I don't want to tear anybody down, but that may be the misunderstanding. Like, we're not trying to be sophisticated here. We're trying, and we're not trying to dilute either. We're trying to distill. That's what physicists really do. And that's harder than it sounds. And especially if you're not used to it. So yes, okay, I'm going to move on. But great question. Please submit for points for that. We're going to move on, move on. Sorry. Oh, okay, I think she got in. Okay, thank you. It was not full. It was a glitch with Classroom. Oh, okay. And I see there's a hand. Huh. Okay. Oh, the person, okay, wait. I see what you're saying. Right, we don't have wait.
Do you mind if I explain it
Yeah,
like a
go,
little
go.
bit?
Okay, go. Okay, yeah.
Yeah, at this point, I don't really care if people know it's me. Um,
Okay.
but so I clicked submit, and then it told me that it was submitted, and I just went into Classroom to kind of like start typing everything for game turn 5 so I can submit it right after class. And I saw that it told me my game turn 4 was missing, which means that even though it told me it's submitted, it apparently didn't submit.
Okay.
So I'm not really sure what's going on with my Classroom, but my Google Drive has plenty of space, so that's not the issue. I feel like it was mainly maybe just like an issue with Classroom itself. I don't really know what happened, but I can't like resubmit it on Classroom because there's no option to do so since it's past the due date,
Well, okay, so
which is
that
why I was asking if I could email it.
right. Okay, got it. All right, totally understand. Okay, one quickly just to make sure we're okay. Can you try, especially now that you've talked and you've obviously participated today, so thank you very much. Can you try right now to just see if something like whether it's game turn 5 or something else, can you just like while can you see if you're able to submit anything else that isn't past the due date now? Like in other words, if the glitch, whatever the glitch was, can we see if it was temporary and resolved and like we're able to move on to other stuff now?
Yeah, I'll type up game turn 5 right now, and then I'll try to submit that to
Okay.
see if it goes through. I'd
Okay.
appreciate if you could let me know if it does, because if in that case, it could just be that like it was a one-time occurrence.
Right. All right. So I've got to move. Right. Exactly. If it was just a one-time thing, then do send me an email and we will retro fix the number 4. If it was just some sort of glitch, like I'll do that in this case and we'll do it after class. Right now, wait, I'll look to see if you're, and obviously I do want to move on in a second, but yeah, we'll solve the,
Yeah,
but wait, so you just tell me, did you just submit something?
no, that's not me.
Wait,
Not yet, anyway.
okay.
Game turn 4 for game turn 4, my attachment is still there. Like my Word file is still there. It's just saying it's missing and that I never submitted it for whatever reason.
Okay, so I can deal with that, but just really quick because I do want to move it with. But try right now to give a game turn 5 or something like that.
Yeah,
Um,
I'm gonna try to do that.
okay, and I'll say to everybody else while you're doing this. I mean, I know we all do want to move on. Just to be clear, also about deadlines and stuff. Yeah, she is right. I mean, Alice is right that that with all the big homework like problem sets and stuff like that, they have due dates, but I don't close the portal on them because you can as long as you get the first draft in on time, you can always keep, submitting the revisions and getting more and more points for the big portals. But she is right. It is true, just to be clear to everybody, on these daily turns they're supposed to be every day, and they're 5 points. They're meant to be a quick daily reflection. So those portals do close at midnight. And in general, you can't. I don't want people going back and retro, especially like I don't like the idea that at the end of the semester someone's going to go back and like try to hand in like 20 of those. That defeats the purpose. So it is true everything Alice is saying that the daily ones you either do by midnight or just forget it and move on with your life. And there's so many of them that obviously everybody's going to miss some of them. But okay, Alice. So, but yes, your five just did come in. I totally see it. So just remind me later with an email, and I'll retro fix the four for you, and we should be good going forward. I mean, you and every but if Zach, okay, wait, I'm sorry, I'm in 85 screens at once, but oh, you're welcome. Thank you. Okay, and to everybody else, what's the benefit to all the rest of you? Just the knowledge here is first thing to check if ever Google seems to be glitchy for you is check your drive. But okay, I want to move on, but no problem. It's a pleasure. Okay, I'm going to change the view on the screen and get to like some math now. So what I'm going to do now is go back. Change. I want to go back. Oh, here we go. Okay, to what's on the board here is where I want to get to today. Um, well, yeah, what's on the board is what I want to get to today. I'm going to back up. I'm going to do this a little bit quickly. I'm going to back up and remind you and go a little bit, expand a little bit more slowly and carefully exactly what we did last Thursday. Last Thursday, we finished problem number 9 from homework 1A. Like in theory, we finally put homework 1A to bed last Thursday, right? We got an answer, 0.116 meters. Answer to what question? To the question at t equals 1, what is x, right? But what I was trying to tell you then, and I want to tell you now, is there's a reason we spent like 2 weeks leading up to that answer. I don't really care about the answer 0.116 meters. What I care about is by the end of that homework assignment, what we really had, sorry, we we had a situation with a mass obeying Hooke's law, on a spring, a mass going back and forth on a spring. And by the end of the whole setup and asking ourselves a bunch of questions like, what does it look when it goes back and forth? Does it conserve energy? What does that look like? What does that mean about speed? What does that mean about acceleration, etc.? We asked all these questions about something oscillating back and forth on a spring. And finally, by the end, we asked, okay, can we just like predict where it is at any given time? Like, can we just like be normal physicists about this? Like, can we ask the standard question, given some time, at what space will we find this mass? And it turns out that that last question is very simple and reasonable to express as a question. I mean, my wife would, I love my wife, but she doesn't like physics. Okay. But if I went up to my wife and said, like, okay, we were in class today, we were trying to figure out if at any given time where this object was, she'd be like, okay, I think that's totally boring, but I get it. Like, I get what you're asking. Well, yes, that's a standard simple physics question. But what it turned out is, in order to answer that question for this situation, um, it suddenly generated some unusual and unexpected level of mathematical sophistication. In other words, what we found, and so we had to do a little work. Sorry, we had to do a little work in order to answer the question in general, what is x as a function of t for a setup like this, for a mass that's obeying Hooke's law? Like, so really what we got at the end of last week was a rule, a mapping, a function. We got x as a function of t given f equals negative kx. Like that's really what, now we did it sort of quickly, but that's a big discovery. It turns out to have really important implications. So I'm going to back up now. I'm going to unpack it. I'm going to do it a little bit more slowly. So this is kind of a review of what we did last time, but then of course I'm going to push it forward. But so if So this is kind of a review. I want to emphasize, even if you wrote it down last Friday, please write this stuff down again. If you did write it down, if it went too fast, good. This will help you because I'm going to go slower. But if you think you got what I said last Friday, then this is an opportunity for you to relax and be like, all right, I think I get the big point. Now let me lean in. Now that I know what the big point is that he made last Friday, let me see if I can follow some of the more nuanced details of it. Like, in other words, this is not actually repetitive. It's meant to expand. Okay, all right, here we go. So what we had. So this is but what I'm saying is this is now a general lesson. It's not really about just exercise number 9 anymore. We're done with that homework sheet. But this is about like what was the point of that homework sheet? Well, the point is this. And I'm not doing the step method as such. I'm just saying, I'm like now I'm teaching because we've already gotten the answer. So what did we know looking at this situation? We knew these things. These would be like our step threes, right? We know F equals MA because it always does. We know F equals negative KX because this is a mass on a spring. We know that the definition of instantaneous acceleration, always in physics and calculus, the definition, triple equal sign, is the second derivative of position with respect to time, right? So these are like step 3 statements right here, all 3 of them, right? So we can put them together. And we know the second statement is F equals negative kx. It's the only force acting in this situation. So we can put these things together, and we did last year. So we can say, okay, fine. So kx equals ma. In other words, sorry, or in other words, k negative kx equals m dx dt squared. And the question is, what we're looking for, what we were looking for then, and what we're looking for in general is we're looking for some rule, some expression that maps t as an independent variable, as an input, to x as the output or dependent variable. We want x as a function of t. No, that's what we wanted last Thursday. That's what we want in general. Note already, you might think of physics as we have problems to solve, so we pick the correct equation and then we plug numbers into the correct equation and we solve our problems. What I'm trying to show you now in Physics 204, and what you're trying to see in the lab that may be new to many of you, is when you really start doing physics, like really, you don't use equations to solve problems. The problem is, can you generate a certain equation? Like we're trying to make equations. We're trying to discover equations. Equations are now the answers to our questions, not the thing we use to get answers to a question. In other words, I'm saying I'm looking for the function. I'm looking for some kind of function of t that will yield x in general. Okay, so given what? Given that negative kx equals m2x dt squared. So the first thing I did last Thursday is I said, ooh, what's intimidating about that is the derivative. So let me lean in. Let me focus my attention on the piece that is unexpected and sort of intimidating, i.e. the derivative. So I isolate it. I have this, right? So I have second derivative of x with respect to t equals negative k over m times x. So this equation is treating x as a dependent variable. I can tell that because it's in the numerator of a derivative. And it's treating t as an independent variable. It's in the denominator. So x and t are the only 2 variables in this equation, and they are properly the dependent and the independent variables. Everything else in this equation, the k and the m, are constants, right? They are just numbers. I mean, in the case of homework 1A, they happen to be the numbers 200 and 0.3. But where they're being left as letters, not because they're variables, they're not variables. They're not going to change. throughout an experiment. It's just that so they're going to stay one steady number. I just don't know what that number is. What I'm really basically saying is this is a statement that would be true for any lab group during lab one. For any lab group, whatever your K is and what your M is, they stay the same throughout the entire oscillation of the spring. But since your K might differ from one lab group to the next, I'm not restricting myself. Okay. So you want to have in your mind what's a variable and what's a constant. So I look at this and I'm like, okay, there is the correct information is there. The X is being treated as a dependent and T is being treated, but the information is packed together in a way that is not useful directly. That is not a prediction. That does not tell me how to predict where X is at any given time. What that says is what the rate of change of X is. It says I can't tell you X, but I can tell you I can tell you about the acceleration of X. I can tell you the rate at which X changes in other words, the second derivative, the rate at which X changes its position in time. I can tell you that, says the equation, and I say, oh, okay, good. Tell me, because I'm used to physics 203. If you tell me what the acceleration is, I can use some kind of equation. Like if I know the rate at which it's changing its speed, um, then presumably I can predict what its speed will be at any given moment. And then from that, I can predict what its position will be at any moment. So I say to this equation, I say, okay, fine. Tell me the acceleration. And from that, I'll figure out the position. But what the equation says is, well, the acceleration, the left-hand side, the rate of change of X is equal to something times X itself, right? This is what I'm slowing down. I said this last Thursday. But I want to say it again. This equation is not giving me X. It's giving me a rate of change of X. That's already kind of interesting. But what's super interesting and at first confusing about it is that it's saying the rate at which X changes is based on X itself. Hold on. I'm saying instead of giving me the variable, it's giving me a rate of change. In fact, a second rate of change of that variable. I want the variable itself. I want the function. It's giving me the derivative. Some of you, I think, in your mind last week might have thought to yourself, okay, so I'm gonna, right? I want the function. I want to predict where is the thing as a function of time. It doesn't tell me that. It tells me the rate at which it's changing where it is. Okay. So I need to go backwards to the function itself. If any of you at any moment last week or right now are thinking, okay, fine. I want the function, but it's giving me the derivative. If you're thinking something like, so I gotta sort of like do derivatives backwards. So do I have to do like anti-derivatives? Can I do like an integral? Could I like integrate this thing twice because it's a second derivative? Couldn't I just like move backwards and integrate? Is that what Yavram's getting at? If that's what you're thinking at all, or last week or right now, if you're thinking anything like, wait, so I've got to run derivatives backwards, I've got to inverse my derivative, and don't I do that by integrating? Is that what I need to do here? If you're thinking that, you're in the right place and you have been paying attention to calculus and you are being smart. If you're thinking, is this something like integration or something? Good for you. You are with me in the conversation. However, it's a little bit harder than that, or it's a little bit more unusual and exotic than that. Because here's the thing. Well, to cut to the chase, the letter right here is not T, it's X, and that makes all the difference. In other words, what we're used to in Physics 203, we're used to being like, oh, if I need to know where something is, if I know the rate of if I know it's gaining speed at like 9.8 meters per second every second, right, which we know in physics, if I know a rate of acceleration per time, if I know how the speed is changing in time, okay, then I can go back. I know that acceleration is the second derivative of position with respect to time. So if I know something like that, I can unwind, I can integrate with respect to time and say, oh, well, if every second it's gaining 9.8 meters per second, then I guess in 3 seconds it'll have like 27 point, whatever, like close to 30 meters per second of speed in 3 seconds. And then, oh, if it's going 30 meters per second in 3 seconds and it started at zero, so it's like average speed would be 15. So I guess I can multiply 15 by 3 and I can predict where it is, like something like that. You can do all that. You can move back. And in effect, you're integrating when you do that. You can move backwards if the rule you were given, if the derivative you were given was expressed as a function of the independent variable of time. Then you can work backwards in time and figure out what's going on. But this is not just an equation with a derivative in it. This is basing the derivative not on the input, but on the output. So that's like circular reasoning. It's saying if you want to know where this thing is, you probably need to know its acceleration. But if you want to know its acceleration, the acceleration is based on where the thing is. If that confused you, you're in the right place. There is something confusing about this. This equation that has a derivative in it, the fact that the derivative is based on the dependent variable, is expressed as a function of the dependent variable rather than the independent, that's why this equation is called, well, here, I'll write on the next page. Okay, when a derivative, when a rate of change of some output is a function not of input, but of output itself, that's called a differential equation. And if you think that sounds a little confusing, you're right. And you're really right. If I were to just make up a random differential equation, just write down like, oh, dyx, chances are it is not solvable. Most just random arbitrary differential equations that we just make up in the hopes of playing with math are not solvable. Because why should they be? It doesn't even sound like it should make any sense. Most are not. But for some reason, some phenomena where the rate of change of output is not based on input, but based on output itself. Sometimes, especially when nature presents them, sometimes they actually work. And it's really weird that they work. And when I say that they work, or I say that they're solvable, what does it mean to solve? Okay, I'm going to say this. To solve a differential equation does not mean to get a number or something. It means to get a function that directly maps output to input and yet satisfies the description of the equation. To solve a differential equation means to find a direct function output equals f of input that meets the description of the jjPHY2 of the differential equation. I mean, of course, I'm going to do that. Now, we did this Thursday. I'm just doing it slowly now. I'm trying to say, and here's a quick example. Here's a quick example. I'm looking at the time. Well, a quick example is like I go to the bank, I ask, hey, how much money is in my interest-bearing savings account? I mean, you've heard this before, but you might not have thought of it this way. I go into a bank, I have an interest-bearing savings, it generates interest. So I say, how much money is in my account? They say, oh, well, that depends on how much interest we added to your account last night. I say, oh, okay, I guess that makes sense because I get interest from you guys. Okay, well, how much interest did you add last night? And they say, well, that depends on how much money is in the account, right? That is an example of a differential equation that almost should not make any sense. How much they add to my money depends, I mean, how much money is in my account depends on how much they added, how much they changed the money by. But what do they base what they change the money by? How much is in there? It's feedback. Any differential equation where the rate of change of the output is based on the output itself feeds back on itself. And so many of those situations don't have an answer. But some, especially if they come from nature, do. The mass on the spring, the fact, I'm saying the rate where it's going depends on its acceleration, but its acceleration depends on where it is. How does that even make any sense? I'm not even sure I would believe that it makes sense, except that I know if you put a timer to the mass on the spring, I mean, if you add a ruler, at any given moment, the spring is somewhere. So something is happening. X is a function of t somehow. So there is a solution to this differential equation. Is there a straightforward, like algorithmic way of finding the solution to a differential equation? No. It doesn't matter if it's the first time you've ever done it or you've done them a million times and you're an expert. It doesn't matter if you're the physicist who's discovering this for the first time or a student in college or you spend your whole life doing these things. There isn't a clear, direct rule for solving them. It's a puzzle to be solved, and many of them are not solvable. We just try things until they work. And we get better and better at trying the more experience we have. I'm saying all this to say, on the one hand, there's entire classes called differential equations because they test and play with all these different differential equations in the world, and they just get better and better at playing with them and developing more and more techniques for solving these puzzles. So there are classes and books devoted to differential equations. But on the other hand, it doesn't mean you have to take any of those classes to be in this one or anything like that, because we're not trying to learn all the differential equations of the world. We're trying to learn the few that matter to us in physics here in the same way that physicists discover them because nature presented them. And so physicists had to just figure out, so I'm saying this is the real deal. What we did last Thursday, in other words, we're trying to find an x as a function of t such that d2x dt squared equals in other words, what we're trying to do, or what we tried to do last Thursday, what I'm going to do again more slowly now is we're looking, what it means to solve. We're looking for some expression that relates x to t such that When you take two derivatives of x, yeah, when you take two derivatives of x with respect to t, when you differentiate twice in time, you get back x times some positive constant times -1. That, and you may want to write that in your notes more clearly than I just said it. We're looking for an x such that when you differentiate it twice, you get back x times some constant times -1. That's what we're looking for. And I'm going to say it a lot. And that's what all of math homework too. I mean, math methods homework too, has a lot of practicing and exercises of it. It's like it, once you get it sort of a bit, it gives you a lot of different practice exercises of this. Um, and notice my language. I'm going to move on and do it again, but notice my language. We're looking for an X such that blah, 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 blah. So this is like going backwards. It is confusing to people when they first, it can be confusing when you first look at it because it's kind of like Jeopardy. I'm giving you an answer and we're sort of looking for the question or something like that. We're not trying to use an equation to get numbers. We're trying to find an equation that meets a certain description. We're trying to find a function that when you differentiate it a certain number of times, it yields a certain result. So we're going to guess and check. I mean, with like we did Thursday, I'm just doing it again, sort of, and then moving on with and then explaining the results. We're going to guess and check, or conjecture and verify, but I really want to emphasize to you that is not because we don't know enough or because I'm assuming we know too much or something. That's what we do. We have to guess and check. There is no straight line approach, but it's still hard science, hard math, or like strict math, strict science, because once we have a guess to work with, checking means taking derivatives of it and seeing what happens. And with derivatives are an algorithm, a procedure. If you've ever felt more comfortable with derivatives than you did with integrals, welcome to the club. Welcome to the world. That's not you missing something. That's everybody. Derivatives are more comfortable because there's rules for them. As long as you know the rules and you practice them, you do it. And when you get the answer, you know you've gotten an answer. You're done. Integrals and this business is puzzle solving, right? But what I'm saying is, so we're going to work on a guess. We're going to come up with a guess, and then we'll know if it's right scientifically, mathematically, because if we differentiate, because we'll differentiate it twice and see what happens. Okay. So, and again, we did this, so I'm doing that. So, so, well, I'm going to say, okay. So what we're looking for now is an x as a function of t, such that if I differentiate it twice in time, I get back itself times a positive constant times -1. That's what I'm looking for. So I say to myself, like I did last Thursday, I say, well, first of all, I've been in the lab and I'm picturing this function is meant to describe something going back and forth and back and forth and back and forth, back and forth smoothly and naturally, like in the real world, and back and forth in a way where it goes forward and then goes back, and its velocities do the same thing. While it's going down and then going up, its velocities are going up and then going down, and its accelerations are going up and then going down. Like I'm looking for some kind of function that goes back and forth like that so I can picture the graph, right? And that's physically. I'm looking for a function that starts somewhere, doesn't start at 0, 0, because then nothing would happen. It starts somewhere and goes back and forth smoothly with all of its derivatives going back and forth smoothly, right? You can already see where this is going. And also, mathematically, I'm thinking I need a function where if I differentiate it twice, I get back itself times some kind of constant times -1. Well, I know from math, I mean, I know what that graph looks like. And I know in math, If I take a derivative of cosine, I get negative sine. If I take the derivative of negative sine, I get negative cosine. So that doesn't prove anything, but it says to me, you know what? Cosine seems like a really good thing to try here. Cosine seems like the simplest thing I could picture that would capture all these properties. So I try some kind of I could try sine also, except sine of zero is zero, right? And that's not, the mass didn't start at zero. Nothing would happen if it did. So cosine is immediately slightly more convenient. Sine could work also, but it's just not as convenient. So I tried something with cosine, but like I said last Thursday, as a scientist, that cosine idea is the right place to start. It's the shape of the function, but it's not, I'm not there yet. That's not really something I could even try to verify yet because the units just don't work. Because this is science. This is the real world. There's measurements this is based on. And you cannot take the cosine of a second. You can only take the cosine of degrees or of radians. And radians is what I really want to get to today. Um, so, I know a lot of you might hate them, but you're familiar with them. I can only take the cosine of radians. Therefore, there's got to be some kind of constant here. There's got to be some kind of constant measured in radians per second that will cancel out the seconds of time and leave radians so I can take the cosine of it, right? If my guess is even reasonable, there's got to be something there measured in that stays still. So I could call it anything. I could call it C for constant. I could call it D for Dan. But I'm, with the benefit of hindsight and with only 20 minutes left, I'm going to use the letter that all physicists tend to use in this context. I'm going to use lowercase omega to stand for this. Now, I have to emphasize, I want by the end of this class today to explain what that omega really means. But at this point, I don't know what it means. It just is a placeholder for something that's measured in radians per second. Because I believe that would have to, some kind. So, okay. Similarly here, there's got to be a placeholder. I mean, there's got to be a constant measured in meters. But this one I already know a little bit more about. This one, I know that cosine, any normal cosine graph ranges between 1 and -1. But this cosine, but I don't want, but the mass on the spring is not going back and forth between the raw number 1 and the raw number -1. It's going back and forth between two positions that were measured in meters. Like it's going back and forth between 0.15 meters and -0.15 meter, or between, in general, like it's going back and forth between x naught and negative x naught, right? So when t is 0, the cosine will return 1. Cosine of 0 is 1. I, I don't want x to be 1. I want it to be 1 times x naught, like 0.15 meters or whatever. So in other words, I want to stretch my entire cosine graph so it's not just between 1 and -1. It's between whatever the initial value is and the negative of that value and measured in meters. So this is my guess, like I said last Thursday. My guess, it doesn't prove anything. The guess that I think could maybe work as a rule, as a mapping of like, I'm guessing that if I want to predict where this mass is at any given moment of time, I'm guessing that it's x naught times the cosine of some number, some constant number times time, right? And if I could plug in all those numbers into a calculator in radian mode, it would spit out where the mass is. If I'm right, if I'm right. So how do I find out if I'm right? So now, we're going to verify. I'm going to tell you now, I know we only have 17 minutes left. What I'm about to do now, and I know I sort of did it last Thursday, but if you want to take out right now your math homework number 2, or you want to look at it at your leisure, what I'm about to do is what the first like 4 exercises on the homework are. It gives you functions. Like on the homework, the very first exercise is this, but instead of saying x naught, it says capital A. And it asks you to take derivatives of these functions, because that's what I'm doing now. I'm going to verify whether or not this function meets the description that it needs to meet. to solve the differential equation. So I'm going to take derivatives of it. Um, I'm just going to say quickly, because I'm concerned about time because we don't have class this Thursday. Like, this is what on your math homework. First of all, I didn't present you with a diagram, but you do want to do the 5-step method. You do want to present diagrams. What diagram would you start off with? A cosine graph, just like right here. Just everything that's it, but instead of labeling it X naught like I did for this purpose, label it A, because that's the letter that's given in the math problem. Okay. And anything else that you're going to use in the math, you want to label in that graph too, including omega. Now, by the end of 15 minutes, hopefully I'm going to tell you more about what omega means and how you would label it in this graph. But just pro tip, you might want to make a note. You're going to want to pay attention enough to understand omega enough to somehow see how to label it in the graph. Okay. So now if I were you, so now I'm going to take derivatives. If I were you, again, I'm just saying this as a pro tip, like, uh, I need to know the step two, the what is the question would be what's the derivative of that X up there? For step three, I'm going to say this quickly. I would write out the chain rule. I would write out that the chain rule is a thing that's true, and that what's true is if you're given the function y equals cosine of x, the derivative is negative sine of x. Like these are two truths that you need from math. And I would give a little guidance on it. Like for the first time you introduce it in your homework, explain them a little. Give me a graph or something. Show why you understand how the chain rule works. You don't have to prove them, but give a little context of explaining the chain rule and trigonometric derivatives at least once in homework. I'm not going to do that right now because I'm trying to move. But if you know those two things, and if you don't, you do want to ask me for help, and there's no shame. Like not now because we're running out of time. But privately, what I'm saying is, given the I'll make a note to remind you. Like given like step three, chain rule and trig derivatives. So step four, the derivative is therefore negative omega x naught sine of omega t. Make a note if you don't follow that, please talk to me. There's no shame. I just can't sort of do it right now. But that's the first derivative, right? If I do the derivative again, the derivative of negative sine is negative cosine, but I have to do chain rule again. So the omega comes out again. So I get this, right? That's a second derivative. But then sorry, there's things in the chat, and I am aware of the time. Sorry. Wait, great question in the chat. I great question about like the simple harmonic definition. I don't think I've given that yet. So I'm going to quickly, great question. I may be misunderstanding it. I'm going to quickly say no, not until this is all established. Like later, I think you can, but I don't think we've established it yet. I think that's where this all is going. I think, but I can talk to you privately after. I think that's a good question. I may be misunderstanding it, but so I have this. This is my second derivative. So what? The key point is that then I notice because I put all the omegas in front. I notice this whole thing here is what I mean by X. This is what I'm conjecturing. So evidently, right? So evidently, if I conjecture that X equals X naught cosine omega t, and I took two derivatives, evidently, what I get is that, right? But that's huge. That you have to follow that. Like I had to notice that X was embedded in there in other words, the second derivative when I took two derivatives of this particular x, I got back that particular x times a positive constant times -1. How do I know omega squared? I don't know what omega is, though, you say. You never explained omega. Like, what is omega? I don't know what omega is yet either, but I know it must, I know omega's being squared here. So no matter what omega is, even if omega is a negative number, it's being squared. So this entire thing is a positive constant. So So remember what we were looking for here in blue at the bottom, we were looking for a function that if you took two derivatives of it, you got back itself times some positive constant times -1. Well, that's what we just got. So something worked. Now you might say, as I did when I first saw this, you might say, wait, but I thought we were supposed to get k over m. And we I thought we were supposed to get negative k. I thought the positive constant was supposed to be k over m times x. Sure, but positive constant means some number. K over m was one number for one group, and it was a different number for a different group. K over m is not literally a number. It stands for a number that doesn't change throughout the experiment, right? K over m meant some kind of positive number that doesn't change throughout the experiment. We just got some positive number that doesn't change throughout the experiment, being the constant of proportionality. And we still don't even know what that thing means. It was just a placeholder. Like we could have called, you see what I'm saying? Like what we needed was for the second derivative of x to return x times some kind of positive constant times -1. So in short, what I'm really saying is we've been saying I don't know what omega is, but apparently we just found out. As long as omega squared is just a name, a different name for what we were already calling k over m. As long as or in other words, as long as omega, whatever it is, happens to be the square root of k over m, then that function solves this differential equation. I'm saying, okay, so what, in a way, what we just learned was two things. We learned that the cosine function is a way to predict where the mass is on the spring for any given moment. But we also learned that the predicting rule is we also learned that the predicting rule is x will depend on cosine of omega t if as long as by omega as long as omega is determined by the stiffness of the spring and the heaviness of the mass, right? So we did just solve the differential equation. Like, so what? Well, two things. Number one, in terms of lab and future problems and all that, the math did not know which lab group you were in. The math doesn't know what the stiffness of your spring is or what the heaviness of your mass is. In fact, the math doesn't even care that there is a K the math doesn't know that there's a piece of metal coiled like this attached to. The math just knows the math. So I'm saying from now on, in general, based on that math, if let Z stand for any. Now, this may be what the direct chat person was saying. From now on, if Z is any variable, if it's theta for the a pendulum string, or if it's E for electric field, or if it's T for temperature, a capital T. From now on, if Z is any dependent variable, any variable that depends on time, if for, you have some reason, whether it's data or mathematics, if you have some reason to believe that the second time derivative of that Z is equal to -1 times some positive constant times Z itself, then we say Z is oscillating. Then the value of Z is going back and forth, back and forth, back and forth harmonically. What do we mean by harmonically? We mean two things. We mean can be described by this expression, Z equals Z naught cosine omega T, where omega is the square root of whatever that positive constant is. Like we're saying that from now on, if something is described by that different, if a value, if a measurement is described by that differential equation, then that measurement is going back and forth, back and forth, back and forth according to cosine of omega time. Omega will be the square root of whatever the constant of proportionality is in the differential equation. And to say that it's going back and forth harmonically, what we really mean by that is will behave exactly like a mass on a spring in all respects. All questions 1 through 9, anything we believed about a mass on a spring is now true for life for anything that we call a harmonic oscillator. Harmonic oscillator means to act just like a mass on a spring. That could be a pendulum, that could be an electric field, that could be a temperature. As long as it's described by that differential equation, then it's a harmonic oscillator and its solution is the cosine thing. So the last thing though is in terms of and that omega will always be the square root of whatever the constant of proportionality is. The last thing for 4 minutes though is okay, but really, what do you mean by omega, Yaverbaum? You keep saying omega is the square root of the what is omega? And so so for a mass on a spring, maybe it turns out omega is equal to stiffness over mass square rooted. For the pendulum in the lab, maybe it turns out to be equal to 9.8 over the length of the pendulum square rooted. It does. It's always equal to like something that has to do with the equipment of your oscillator. But what does it mean? What does omega mean? Well, like what does it mean to measure radians per second? The bottom line is this. Radian is a measurement of angle. What does angle have to do with, like radian is a measurement of angle. What does angle have to do with something going back and forth, back and forth, back and forth? Listen close to this. I know we have 3 minutes. We'll land the plane in 3 minutes, but listen close to this. An angle, and maybe write it down. An angle is a fraction of a circle. We are going to use the mathematics of circles to describe the physics of cycles. The reason angles come up is like a right angle, for example, is a quarter of a circle. 180 degree, it doesn't matter whether you call them in degrees or radians or whatever. What an angle is a section of a circle. An angle is an arc length measured in meters divided by a radius measured in meters. You know that if you go around a full circle, the angle of a full circle is the full arc length around a full circle known as a circumference, or in other words, 2 pi r, divided by the radius of that circle. To go around a full circle is to go 2 pi radians. 2 pi radians is, in math, 1 full circle. In physics, 1 cycle. Okay? What omega is how many radians per second something is doing. What does that mean? If you have a mass going back and forth on a spring, if you think of each cycle, each round trip there and back as 2 pi radians, then what omega really is just 2 pi times the number of full cycles the thing makes, otherwise known as standard frequency. I'm literally saying, if I know we've 1 minute, I'm literally saying if a mass goes there and back 3 times per second, if it does 3 cycles per second, Well, we say each one of those cycles has 2 pi radians in it. So we would say the angular frequency of a mass going back and forth is 6 pi radians per second. It sounds completely abstract, but it's just because we're taking math that we already know for circles and imposing them and using that math conveniently to describe and predict cycles. If something makes a full cycle a second, then it makes 2 pi radians per second. If it makes 3 cycles per second, it's making 6 pi radians per second. 1 cycle per second is known as 1 hertz. And the last thing I'm going to say, and I'm going to put the pen down, is the opposite of hertz, the opposite of standard frequency is period, right? If, in other words, if standard frequency is cycles per second, then period is seconds per cycle. So bottom line, I'm saying this is 3 different ways to explain, to identify the one constant characteristic of a harmonic oscillator. If I say that it does 3 cycles per second, if I say it does 6 pi radians per second, what that really means is it does 3 cycles per second, or otherwise known as 3 hertz. And that means it takes 1/3 of a second to do a cycle. Period, standard frequency, angular frequency. If you know one, you automatically know the other 2. Period is the easiest one to picture and measure in the lab. Angular frequency is the easiest one just to make mathematical predictions and solve differential equations with. Omega comes out of the math, capital T comes out of the lab, lowercase f is the bridge between the 2. Angular frequency, standard frequency, period. 3 interlocked, interrelated ways to describe how rapidly an oscillator is completing cycles. So omega is angular frequency. But when we say omega equals square root of k over m for a mass on a spring, we mean, the stiffer the spring is and the lighter the mass, the faster the thing will go back and forth and back and forth. Or if we say omega is square root of g over L for a pendulum, we mean, the stronger the gravity and the shorter the string, the faster the pendulum will go back and forth and back and forth. Omega is cycling rate, just measured in radians rather than straight cycles. There's 2 pi radians to 1 cycle. That is it. That's all we needed to know for everything. Okay, I'm done. You can go. Please go. Have a great long week. But I'm here if you want to ask. I know that went fast at the answer. If you want to ask any questions or anything, I'm here. But have a great week. And we do not have class until next Thursday. That's right. It's weird, but it's true. Right. I will see you a week from this Thursday. But you can email me or whatever in the meantime. Okay, thank you. Yes, thank you. Have a great week. Yes.
Have a good day, Professor.
Great day. Thank you. Bye.